The goal of this lab is to find the mass of the black hole given the trajectory of the star orbiting it. To do this, we're going to run through the entire model and find the mass at the end of the program. Here's what we're given. We're given the x and y coordinates of the star through each time step in a CSV file right here. We're given the mass of the star that we set to star.m, and we're giving the position of the black hole, which we set to blackhole.pos. We set the delta t to 86,400, which is how many seconds there are in one Earth day. We changed this read CSV part right here to what we named the CSV file that we downloaded from the website so that it reads all of this information right here. We edited the delta y to get the change in the y coordinate through each time step. We set the p initial and p final to the star.m, which is the mass of the star, times the velocity, the initial right here and the final right here. And then we set delta v to the v final minus v initial, delta p, p final minus p initial, and then dp dt, just delta p over delta t. And fnet equals dp dt, but you already knew that. With these equations right here, we know that dp dt equals dp dt parallel plus dp dt perpendicular, and that dp dt parallel is d magnitude p over dt times p hat. So to find dp dt parallel, we have to introduce the variable p hat and make it p initial over the magnitude of p initial, which is p hat. And then we have a variable right here, which we do put the delta magnitude, which is magnitude of p final minus magnitude of p initial over delta t, which gives us this part right here. So now that we have these two, we do d mag p dt times p hat, and that gives us dp dt parallel. And you already know that fnet parallel equals dp dt parallel. So now that we have dp dt and dp dt parallel, we can find dp dt perpendicular by subtracting dp dt parallel from dp dt right here. And fnet perpendicular equals dp dt perpendicular. Now we use all of this information to find the mass of the black hole that we were trying to find. So we go and use this formula right here, which is the force of gravity, which is the only force acting on the star by the black hole, to find the mass of the black hole. So we know we can find the force because we know dp dt. We know big G, which is the gravity constant of 6.7 times 10 to the negative 11. And we know R through here, which is the magnitude of the star position minus the black hole position. And we know the mass of the star. So the only thing we don't know is the mass of the black hole. So we take that formula and derive this formula right here, the magnitude of fnet times r squared over big G times the mass of the star. And that should give us the black hole mass. And we print that right here. Let's see what this looks like when we run it. Okay, so This represents the star. Obviously, this is the black hole. The yellow arrow is the net force acting on the star by the black hole. The blue arrow is the perpendicular force, and the black arrow represents the parallel force. So this is all making sense. And then right here, this is where we printed our black hole mass, 2.5756 times 10 to the 31. That looks about right.
How do you say this thing?
So what does this mean? Why are FNet and DPDT different while they're the same numbers and say the same thing, really? FNet is the force that affects the entire system and makes everything change, while DPDT is you find the difference in momentum to describe the changes in the system. So, in other words, FNet is the cause of everything in the system, and DPDT is more of an observation of the causes, because you find DPDT to calculate the force. So, what if, imagine the black hole whose mass you found was removed and a different black hole was placed in the same location. Assume the motion of the observed star remains unchanged and is affected only by the gravitational force of the new black hole. Could you tell the difference? In other words, is it possible for you to find a value for the mass of the new black hole that is different from the mass you found for the original one? Well, if everything is unchanged, that means that the new black hole would have the same mass as the old black hole. Because if the mass were smaller, then the force acting on the star would be smaller and the trajectory would be wider. And if the mass was larger, then the force would be larger and the trajectory would be tighter around the black hole. So that's my lab.